All right, so today we're talking about a line of best fit. We've created a graph here, and the first based on this table. And the first thing I want to talk about is when you have a table, how do we label our X and Y axis? How do we know what each axis stands for? The first question you're going to ask yourself is, what is this table is implying something. And my question is what is the depender in this relationship? What is the depender in this relationship? They're trying to imply something. Yes. That the brain weight and the life, what? What's dependent on what? So a person's brain depends on how long they live. What do you think?
I think the life depends on the brain weight.
Okay, she's saying life depends on brain weight. Why do you think one's right or one's wrong? What makes this correct or not correct? Yes.
Since they have a heavier brain, it's less if they have more knowledge, it means they can be smarter if you look at brain weight doesn't matter.
Okay, go on.
I feel like both can be dependent on each other.
No. No, this is a relationship, and I'm asking you, what is the depender? What depends on the other? I'm telling you, in algebra, we're working with dependent relationships. So I'm asking you, which is the weight of the brain dependent on life, or is life dependent on the weight of the brain? What do you think, Rebecca?
I think the brain weight depends on the max life because X is always like time it can have.
Okay, but you're trying to go too much to the algebra. I want to know why. Charlie, your thoughts?
I think that the brain weight is the depender, or I think that the max life is a depender for that brain weight because it just looks like when the brain weight is like more, it tends to have a bigger, a longer lifespan.
Okay, so I've listened to everybody, and now really what this table is trying to say, and in statistics, we could try and make a statement about anything. And what they're saying here is, the reason why I say it's not weight depends on life is because when you're born, they don't measure your brain and go, okay, you're going to live 8.2 years. And now this brain, because it's bigger, you're going to live 80 years. And then this brain, I can measure it. So weight, the brain weight does not depend on the lifespan, but rather what they're trying to say is the bigger the brain, the longer you live. So lifespan depends on how big your brain is. Does that make sense?
Yeah.
Now, once you determine what's dependent, that becomes your why. So what did we just say is the depender? Life depends on the size of your brain, lifespan. So the lifespan, since that's the depender, that's going to be your why. Okay? In this case. So we're going to call the y lifespan, and then the x would really have to do with brain weight. Now, you'll notice that I don't have to have the same increments down here as I have here, because this really represents brain weight, and this really represents lifespan. They're different quantities, just like we did before a few minutes ago in the warm-up, and we had these increasing by 10. Do you remember that? And these were increasing by 1. Time was increasing by years. The Y was increasing by gallons. Do you understand? Because they're two different quantities, they don't need to be the same scale. They just have to be consistent. So on the x-axis, we have to make note that we need to go from 0.4 to 440. So the best increments might be by 50. Does that make sense? So you're going to label yours, and you have to label with what the X represents, brain weight. And you'll notice I'm going by hundreds, but really I'm going by 50s. Because here's 50, and then I don't write every single one because I don't have room and it's hard to read. But it's really increasing by 50s, right? So I want you to label that now. Go. All right, now let's do our y-axis. Our y-axis is going to represent lifespan. Notice we have to go between 3 and 2/10 and 50. Do I need to go by 50s? If I do that here, then all of my data is going to be in this area. I'm not going to use my graph. Do you understand what I'm saying? Yes. So let's go by 5s. Okay? And I'm just going to label every other one so it's easy to read. We're labeling by 5s. Go. Or by 10s, every other one. Now what I'd like you to do is plot each point. I'm going to show you the first two. So notice this. I'm going to go over less than half, 0.4, and go up 3.2. And it'll be somewhere around there, less than 5. Notice the next one, I'm going over about 50, a little more, and I'm going just up to the 10. I'm not labeling these points, I'm just plotting the points. I want all of you to do it exactly as I've been doing here. We're just kind of estimating. 150, and then I'm going to go up to 20, just a little bit above. Okay? Okay, I want you to pause it and finish the plotting the points. Do not label any points. Okay, so now I'm going to plot the points. You can check your work. It doesn't need to be exact because these are all estimated. And, oops. All right, so now what do we notice? What do we notice? What shape does it make? What shape does this make? Anybody? Go. What shape?
Kind of like a squiggly line, kind of.
Kind of like a line. Okay? You shouldn't have connected these dots, but you can see they are moving in the shape of a line. That's what we call a linear trend. That's what we call a linear trend. Does anybody know what kind of graph this is called? What? No? It is making a line trend. So yes.
Scatter plot?
It's a scatter plot because the data is scattered all over. Okay? Now, we look at the scatter plot, and one of the things we'd like to look at, this is real data. We want to look at the trend. This is creating, it looks like kind of a line. So we say the trend is increasing, it starts low, and it's gaining. Also, if you looked at the bigger the animal got, the longer the lifespan. So as one's increasing, so is the other. And it created kind of a line. It creates, like I said, it has a linear trend. And this is what we call a line of best fit. Now, we're going to take like a ruler, and we're going to draw a line. Now, where does the line go? We're going to pretend that this is a piece of metal, this ruler, and that all of these are magnets. Where would I place it so I would get the most magnets? Would I place it here?
No.
Would I place it here?
No.
Would I place it down here?
No.
Up here?
No.
Kind of.
No. Okay, I'm going to try and place it basically in the middle of all those points. Okay, even that's slightly off. What I want to do is kind of place my ruler where I have equal amount of points on top and underneath. Okay? So I'm going to place it. Are you guys clear on that? So what have we done so far? We plotted our points. Okay? Step 1, we plot our points. Step 2, we draw a line of best fit. That's what we call our line of best fit. It doesn't connect the dots. It's just a line that goes through with equal amount on top and below. Next. The next thing you're going to do is you're going to take 2 points off that line. Okay? You're going to take 2 points off that line, spread very far apart. Okay, so I'm taking that 50, 10. And then notice right here, I'm taking, that is 450, 50. Now, when I have 2 points, what do I have the ability to find? A slope. So we're going to do that. Now, one more time. Look at my line of best fit. I do not necessarily have to be on exactly one of those dots. I can be close. I can take a point right here. I could take a point here. I could take a point here. So this is not going to be, it's not going to be exact. Your answer and your answer might not be exactly the same because it's real data. And when you take 2 points, it might not be the same as Eugene's 2 points. Does that make sense? But it should be close. So I'm going to take the 2 points and we're going to try and find the slope. We're going to use our slope formula. You should be doing this with me. M equals y2 minus y1 over x2 minus x1. And I'm going to say 50 minus 10 over 450 minus 50. Are we clear on that? You should have this written down because it's going to be a lot tonight. Okay. In the numerator, what am I left with? 40. In the denominator?
40.
So, can I reduce it?
1/10.
Okay. I'm going to reduce it to 1/10. And you will notice as soon as I put real data in, what did I start using? About sign. An about sign. It's approximated. Okay? So it's really about equal to 1/10. Now, more than likely, you're going to be converting that to a decimal. But let's talk about what we talked about earlier. Didn't we say that the numerator is like the change in the y? Yes or no? And that the denominator is the change in the x? And the change in the y on this is, the y really we were talking about lifespan, right? And in the x, what were we talking about? The brain size. So when you get 1/10, 1/10, when I ask you to identify the slope, it's 1/10. But when I ask you to interpret the slope, what can you tell me? Dayasha?
The life is 1 year. They have
What depends on what? Isaiah?
For every 10 ounces of,
It wasn't ounces, it was grams.
for every 10 grams of brain weight is equivalent to 1 life. Or
One-
1 year.
1 year. So again, if a brain size is 10 grams, you're probably going to have a year, it will give them a year of life. But if a brain weight is like 80 grams, you're going to end up with probably about 80 years of life, right? Wait. 10 grams is 1 year. 80 grams is 8 years. So, does that make sense? Okay. Sorry, my math was wrong. What? What?
It's a lot of brains. A lot of brains.
Okay. All right. But in all likelihood, when you're doing these line of best fits, these numbers are not friendly. They are ugly. So you're more than likely going to convert to the decimal. You're going to be using a calculator. So once I know my slope is 0.1, or for every every 10 grams of brain weight. That means they're going to live 1 year. What else do I need? Yep. I need a y-intercept. So I'm going to use my y equals mx plus b. I'm substituting in. I'm going to substitute this in for my m. And I'm going to use this point. So that means 10 is about equal to 0.1 times 50. You should be writing all of this. And I don't know my b. I'm going to solve for b. So 10 is about equal to, that makes, I'm going to move the decimal once, 5 plus b. Subtract the 5, subtract the 5. 5 is about equal to b. So now what am I doing? What is the equation now? What is the equation? Charlie?
Y is about equal to 0.1x
Plus 5. Now, what you've just done with that linear trend of data is make an equation that establishes a pattern that relates brain size to lifespan. Now, in statistics, when we did this originally, we only really took how many people in the sample, or how many, they call it how much in the sample space. You've got like 8 different animals. What they're trying to do is make a statement saying, I believe that brain size has to do with lifespan. They're not going to be able to test every kind of animal or species, but if we can make this for a small sample space, we can predict outside of the data. How do we do that? We make an equation that represents the data. And now we can use that and substitute in new data. So make the equation, and we end up here. Now, here's what we just did by hand. When you plug this into a graphing calculator, you can put in a full table of the real data. And they will take it and they will make an equation of their own. And that's what we call the actual. Now, it's not exactly actual because it's a small sample space. But it's as close as you can get to the data. Okay? So, how far are we off in our slope? Evan? Yeah, about 3 thousandths. No, actually 0.003. So we're about 3 thousandths off in our slope, and we're about 4/10 off in our y-intercept. Do you understand? It's not exact, but it's pretty darn close. Is everybody clear on that? Yes. Stop. Don't even go there. I'm not there. So now, what do we say about the first one? Is there a linear trend on point A? Everybody? No. Okay, what about B? Yes. There is a linear trend? No. Does it make a line? I asked you if there's a linear trend on B. It absolutely does not. Shh. Okay, on C. Yes. Okay, and this is a decreasing trend because it starts high and goes low. Imagine if this is money. We read left to right. I'm losing my money. We don't want our money in that graph. D, is it a linear trend? No. No. So we can't write an equation to represent that. But this one we can. This one, no, this one we can. Can we do it here? Yes. And what about here? It's going to be, it's a linear trend, but it might be kind of tough. Yes.
It's like, let's say on the homework.
Stop going to the homework and stop asking that question. I promise I will get there. Okay. So now, when you find the line of best fit, okay, I'm going to remind you, here are some things to think about. If there is an outlier, this is a piece of data that's not like the rest of the weight of the data. For instance, if every time you've ever taken a test, you're a straight A student, and then you walk into my class one day, you've been up all night, throwing up, and you come in here because you want to take that algebra test and you get 5% because you had no sleep and you can't think. If you've had straight A's all the way through, do you think I should drop your grade, one full grade, because you got one close to having a 0? Do you think that describes you as a student being a B student? Or really are you mostly an A student? Right? One grade of like 0. Is that really gonna, do you think that describes you, or do you think that the person that walked in and took 10 tests that got A's, I should give them the A? Because what happens if you get a 0, it's gonna drop your grade at least 1 grade, if not 2. So my question to you is, I need you to get opinionated here. What do you think is the better idea of that student? Are they really an A student or are they a B student? Right, they had one bad day. Have you ever had a teacher that dropped your lowest grade?
Yes.
Okay, that is because they are dropping the outlier. They allow you one bad day. So we drop the outlier because it really weighs down the data. Really weighs it down. Okay? So we're going to ignore our outliers. Next, you do not have to go through any of the points when you draw your line of best fit. You should basically make sure you have equal number of points above and below the line. Not like this. Not like this. Not like this. But here, where you're going through it. Okay, questions? All right, when you choose your 2 points, this is going to be very important. When you choose your 2 points, if you choose them close together, look what's going to happen to your line. Do you see that? It really moves it. So you really need to choose points that are far apart. So you want, we call that being a sufficient spread. Are there any questions? You got to pick your points apart. So, one more time, let's go through what we're talking about. We're going to plot the points. We're going to draw a line of best fit. We're going to pick 2 points, and that gives me the ability to find what? Slope. And then once I find the slope, I can either use point slope or y equals mx plus b to find the y-intercept and write the equation of the line. Does that make sense? Okay. I'm going to pause this now, and I'm going to go to the book work, and we're going to work on one problem out of the book. Okay. Now, what this linear equation allows us to do is, what happens when you have a human brain? Go outside of the data. Does that make sense? What happens when you have, something that's really outside of whatever you're doing? Okay, so I'm going to... Okay, here we go, number 2. Shh. It says... a temperature of 0 degrees Celsius is the same as 32 degrees Fahrenheit. Now the directions up top said assume a linear relationship fits each data set. A temperature of 0 degrees Celsius is the same as 32 degrees Fahrenheit. A temperature of 10 degrees Celsius is the same as 50 degrees Fahrenheit. Use the ordered pair CF. CF. So I'm doing C, comma, F. Okay? Isn't this like our X and this is like our Y?
Yeah.
Okay, so what are the 2 data points they gave me? Yep.
32 and 0.
I need it in order that they gave it to me. It's 0, comma, 32 because it's Celsius, comma, Fahrenheit. And what would be the next one? Go. Comma. Okay, now what do we have the ability to do? Yep. Find the slope. M equals y2 minus y1 over x2 minus x1. So now I'm going to say, let's call this point 1 and point 2. It's 50 minus 32 over 10 minus 0, which is 18 over 10. Now this reduces to 9 over 5. So I'm using that 9 over 5. M equals. Now I'm going to use that. And I've got to use M equals 9 over 5. I'm going to use this point. Okay? 0, 32. What method did I say I like to use? How about point slope? Right? So I'm going to do, are you okay, Elizabeth? Y minus y1 equals M times x minus x1. Now, I'm doing y minus 32 equals 9/5 times x minus 0. It simplifies to y, you know what? Yeah, we're not there yet. Y minus 32 equals 9/5 x. Are you guys with me?
Yes.
Add 32. Add 32. Y equals 9/5 x plus 32. Now, the thing I want you to remember is we need to finish this. Your x is really a what? C. And this is really a F, right? So I'd like you to write it in terms of C and F. Okay, now, that's part A. Right there is part A. Okay? Part B says, now let's use it and find something outside the data. Use the linear equation to find the temperature Fahrenheit when the temperature is 30 degrees Celsius. So where do I substitute the 30 degrees? Yes.
For the C, so it'd be F equals 9 over 5 times 30 plus 32.
Okay, and I'm doing 1, and we're doing 6, and it becomes Fahrenheit is equal to 54 plus 32. So Fahrenheit is equal to 86 degrees. And don't forget your degrees. So here is part B, here is part A. Are you guys with me? Okay, write the equation. When finding 2 points, we can find the slope. After we find the slope, use point slope or y equals mx plus b to write the equation. Then part B is use the piece of data and substitute it in. You only have 9 more questions to do. And I am here after school. That's the end of the recording.